Hello everyone. So today we're going to get our first official introduction to the normal distribution. This is the so-called bell curve, and it's almost like a kind of mascot, if you will, for statistics in many ways. And we'll see that this is typically used in inferential statistics as a model for how to basically shortcut around having to do simulations like we have been doing for the last couple of weeks. So in a sense, the normal distribution is a way to figure out what a sampling distribution would look like in the long run if we were able to do many, many thousands of simulations. And to use the normal distribution as a model for how these simulations would look in the long run, we need to define a couple of terms. So one that we'll see is called the standard error, and another aspect that we'll have to consider is the fact that the normal distribution is not always a good mathematical model for how our simulations would look in the long run, and the circumstances under which the normal distribution is a good model are defined by something called the central limit theorem. So that's something else we'll encounter today. But when we are able to use the normal distribution as a mathematical model for a sampling distribution, that means we can use it to do the two things that we've been doing so far in inferential statistics. We can use it to construct a confidence interval, and we can use it to conduct a test of a null hypothesis. So all of those things are on the docket for today. So to get right into it, you may have noticed these are a couple of examples from the book. Here's an example of what we did in our lab last week, where we looked at the outcome of Milgram's experiment. So we used bootstrapping to simulate how different versions of his experiment might have turned out in order to construct a confidence interval for the proportion of people in the population who would obey in his experiment. And you'll notice that they all kind of have something that looks sort of like a bell shape, this little dark line here that I've drawn over top of all of these different sampling distributions. And just to kind of situate ourselves, as a reminder, what all of these are histograms that are called sampling distributions, because what they represent is the relative frequency with which different proportions or differences in proportions might have turned out under different assumptions. For example, one assumption might be that the null hypothesis is true, in which case we can look at the distribution of differences in proportions that we might expect if that were true. Or another assumption might be that our sample is representative of the population. That's what we did for confidence intervals. And we can look at the relative frequency with which different proportions would have turned out, and use that to construct a confidence interval like we did with the Milgram obedience study. And so this shape, this bell shape, basically reflects the fact that across many simulated samples, some sample statistics happen more often than others. In other words, the ones corresponding to the higher bars are ones that we expect to see more often. But why is that? Well, let's take a kind of concrete example here to see why that is. So let's imagine that we sample 4 people at random and ask them a question. And this is a simple yes or no question. And in the population, let's say that exactly half of those people would say yes and half would say no. So if that's the case, what we can do is imagine, say, sitting those 4 people down at a table, represented here by these little gray squares, and figuring out, well, okay, how many different arrangements of those people would result in different numbers of yes responses, and therefore different proportions of yes responses. So as we can see, there's only one way to get all no's or all yeses. Those are the 0 and the 4 over here. That's if everyone responds in exactly the same way. There are 4 different ways that we can have one person who says yes and 3 people who say no. So that's this column over here. There are also 4 different ways that we can have um, 1 person say no and 3 people say yes. That's this column here. And finally, there are 6 different ways that we can have an even split. 2 people saying yes and 2 people saying no. And what we can see from this is that there are more ways to get 2 out of 4 yeses than any of the other numbers. Fewer ways to get either 1/4 or 3/4 yeses, and only 1 way to get either 0 or 1 proportion of yes responses. And because all of these possible samples are equally likely, now this isn't going to be true, as we'll see later, if the population proportion is not 0.5, but because each of these possible outcomes here, all these different arrangements here shown in the table, are all equally likely, this sampling distribution has a bell-like shape, as you can kind of see, and it's centered around 2 out of 4. So to generalize that to what we have been doing so far, as a reminder, bootstrapping and random permutation were ways that we could model how a sample might have turned out differently. And most of the time, those imaginary data sets that we simulate would look a lot like what either the null hypothesis would say, if we're doing random permutation, or like our original sample, if we're doing bootstrapping. But sometimes, by chance, they might end up looking very different. So to bring us back to this picture here, most of the time we'll end up, when we're doing simulations, we'll end up kind of near the middle, like so. But some of the time, on occasion, we'll end up in the tails, either extremely low or extremely high. And when we do many, many simulations and keep track of how often each of those different outcomes occurs, then this produces a histogram that looks like this sort of bell shape, where there's sort of a hump in the middle, where all of the kind of typical data sets tend to fall, and then tails stretching out to either side, where the more rare or unusual data sets tend to fall. And the normal distribution is simply a mathematical model of this bell curve shape. So we've talked about in the past the idea of kind of laying a wet, stretchy noodle on top of a histogram to sort of get a sense of its general shape, even if it's a little janky looking. And the normal distribution is basically that. It's a particular kind of wet noodle that we can lay over top of our histogram. So just to make that a little bit more concrete, here again we're getting back to an example here. Looks like kind of what we did with our M&Ms from a couple weeks ago. And one thing that we did with that was to try and use bootstrapping to simulate how different bags of M&Ms might have turned out, with the aim of figuring out what plausible values of the proportion of blue M&Ms might be for, say, different types of M&Ms. So we started with our original sample over here, over on the left. We used bootstrapping to simulate many possible samples we could have observed, assuming that our original sample is at least representative of the broader population of M&Ms. And then use that to construct a sampling distribution, and found the middle 95% of the results, and we're able to use that to construct a confidence interval for the population proportion. The trick that we're going to be doing today is, rather than go through this process of doing many hundreds or thousands of simulations like this, we can sometimes take a shortcut. By which I mean we can figure out mathematically what the mean and standard deviation of this sampling distribution would be if we had conducted many, many different simulations like this. And knowing that mean and standard deviation allows us to use the normal distributions, that's this dark line here, to do all the same things that we would have done with our sampling distribution that we constructed with simulation. In other words, we can use this shape to do things like figure out a confidence interval or test a null hypothesis. But you can see that this bell curve shape, although it is often a close approximation to what we would obtain from many simulations, it's not always going to be exactly on top of it, right? So that's another thing that we're going to be taking a look at. That's that idea of the central limit theorem that I mentioned at the beginning. So in other words, there are conditions or circumstances under which the normal distribution is going to be a good fit to what we would get from a bunch of simulations, but there are circumstances in which it's not going to be a good fit. Now, it's sometimes the case that people will say that, oh, the normal distribution, this bell-shaped curve, is called normal because it occurs often in the real world, and that's sort of true. There are indeed some variables in real life that are approximately normally distributed. So a lot of physical quantities have this property. So say like the birth weight of infants here. This is on the left. The distribution of adult heights of men and women in the United States have a kind of bell-like shape. Another interesting thing is that actually daily changes in stock values also have an approximate bell shape kind of curve, as we can see in a couple of these histograms here. Although it's interesting to note that these curves, although they're sort of bell-like, actually do have slightly longer tails than the normal distribution would imply. In fact, that mismatch between the sort of weight in the tails of the normal distribution and actual stock changes in the real stock market was in part the reason for the 2008 financial collapse, because financial analysts were using the normal distribution as a model in a situation where it was actually not appropriate to do so, and it led them to make wrong predictions about the relative frequency with which they would expect to see extreme changes in stock values. So the fact that they failed to account for that with their model ended up plunging the entire economy into recession for many years. So again, this may seem like kind of an arcane mathematical point, but it in fact has important real-world consequences of making sure that our choice of mathematical model is appropriate to the application. And so again, that's going to be our friend, the central limit theorem, that we'll meet in a few minutes, that will let us know whether we're in a circumstance when we can use the normal distribution versus not. Now, I've been talking about the normal distribution as a shape or a curve, and indeed that is what it really is, because it's really all about this particular shape that has this nice little hump in the middle and is nice and symmetrical around. And so when we're talking about the normal distribution, we're kind of talking about almost an entire family of curves, an entire family of shapes that all have this same look to them. But in any particular application, even though they all have the same shape, they have, say, different centers and different degrees of variability. And this corresponds to our measures of central tendency and variability that we've talked about before, namely the mean and the standard deviation. So this is just to give you a sense of what the formula for this curve looks like. It's somewhat ugly, I suppose, but and we'll never need to see it again, but I just want to point out that integral to this formula are the mean, so that's written out here with the Greek letter mu, so the blue and red distributions here have the same mean, whereas the green distribution here has a higher mean than either of them. And the spread is described in terms of the standard deviation. So the blue distribution here has the smallest standard deviation. It's the narrowest distribution, even though it has the same mean as this red distribution here, which is wider. But the red and green distributions actually have the same standard deviation, so they've got the same degree of spread. And we can kind of see this here in this little cute animation prepared by Matt Crump, showing the center of the normal distribution being sort of shifted around. And yeah, so the center of this of any particular application of the normal distribution is given by its mean, and I will throw this out to you to think about. So is the mean of the normal distribution the same or different as its median or mode? So like I say, I'll let you think about that one. And to kind of figure out that answer may help to think about what the shape of the normal distribution is. And over here, there's another animation from Matt Crump. The spread of the normal distribution is governed by its standard deviation. So here we're seeing a normal distribution with the same mean, but increasing standard deviation. You can see that it sort of begins with a very narrow, peaky looking distribution, and then kind of spreads itself out, sort of like sort of like silly putty or something. Yeah, when you drop it on the ground and it splays out, sort of like this. So that's what it looks like when we keep the mean of this normal distribution constant, but increase its standard deviation or spread. Now, because the normal distribution is really all about just the shape of a curve, and it's really most useful in terms of describing relative frequencies. So we often talk about things, particular, say, values or observations with respect to where it falls on this curve. In other words, its position relative to, say, the mean, in terms of units of standard deviation. So let me give you some examples here. So we've talked about before that subject scores on SAT exams are standardized, and by standardized I mean that across the population they are constructed in such a way that the scores are distributed in an approximately normal form, so they kind of have this shape, and they have a mean that is exactly 500 and a standard deviation that's exactly 100. Now, we could also, as I showed a little bit earlier, use the same shape to describe the distribution of, say, adult male heights in the United States, which have a mean of 69 inches and a standard deviation of 6 inches. So the point here is that both SAT subject scores and adult male heights can be described as being distributed in a kind of normal or bell-shaped way, but what accounts for the difference between them is the fact that they have different means and different standard deviations. That's what sort of gets you from just having a shape to actually describing a distribution of a real range of observed values. And when we are describing, say, where someone falls on a curve like this, what we often do is describe it in terms of what we call a z-score. And a z-score basically tells us how unusual an observation is relative to the mean and standard deviation of this normal distribution. And a z-score is defined as the observed value minus the mean, so that's its deviation from the mean, remember the deviation from before, and then we divide that by the standard deviation. So we could kind of use our mathematical shorthand to write it out like this, but x minus mu over sigma, but yeah, remember that's just a shorthand for these descriptions of real meaningful quantities here. So the observed value minus the mean divided by the standard deviation. And this gives us something that's kind of similar to the Pearson correlation coefficient in that it's something that has both a magnitude and a sign. So the magnitude of a z-score tells us how far the observation is from the mean in terms of the number of standard deviations away from the mean, so in units of standard deviation. The sign of the z-score tells us whether the observation is either above the mean or below the mean. So, for example, if you score 750 on an SAT subject score, you would have a z-score of, let's see here, 1, 2.5, because you are 2.5 standard deviations away from the mean, and it's positive because you are above the mean. On the other hand, if you were in, say, let's say 300, if you scored 300 on an SAT subject score, then you would have a z-score of -2. So, because you are 2 standard deviations below the mean SAT subject score of 500. Similarly, if you're an adult male and you're, say, 78 inches tall, then you would have your height would have a z-score of 1.5 because you are 1.5 standard deviations above the mean height of 69 inches. Now, an interesting thing about the normal distribution is that because of its shape here, if we imagine the height of this curve at any point as defining the relative frequency with which we would expect to see a particular value, then we can say what proportion of observations would be within a certain number of standard deviations from that mean. In particular, we would expect about 68% of people to fall within one standard deviation of the mean, so either one standard to fall between, say, one standard deviation below or one standard deviation above. And so that means that for SAT subject scores, we expect about 68% of people to score between 400 and 600. We expect about 95% of people to score between 300 and 700. And nearly everyone, 99.7% of people, would score between 200 and 800. And so this may begin to look a little bit familiar because, in fact, this is the same kind of procedure that we used to construct a confidence interval, right? We built a histogram describing the sampling distribution of basically the sample statistics we might have seen across many different simulated data sets. And we found the middle, say 95% or 90%, whatever it was, but we found the middle of that distribution. And that defined for us the range of values that we thought were plausible for an unknown population parameter, given whatever we happen to observe. And so, we already begin to see how the normal distribution might be relatively useful for us. Now, just to make sure that we keep this clear before we move on, the reason why we can say this is because we are treating the height of this curve as if it was a bar in a histogram. In other words, we're saying, the fact that this part of the curve is higher than this part of the curve means that we expect to see values like this more often than values like this. And so when we say that 95% of observations will fall within 2 standard deviations of the mean, that is to say 95% of observations should have a z-score that's between -2 and +2, what we're saying is that the total height of all the little bars that make up this curve amounts to 95% of the total height of all the bars. So yeah, let's actually use that now in a concrete example. So last week in our lab we used bootstrapping to construct a sampling distribution for the proportion of people who would obey in Stanley Milgram's experiment. We used it to find a 95% confidence interval for the population proportion, and this is one way that your sampling distributions might have turned out. Yours may look a little bit different from this one here just due to the randomness involved, but it would probably look something like this anyway. You can see it doesn't quite have a kind of clear bell shape, although it has something that's sort of reminiscent of a bell shape. And the mean of this distribution here is about 0.7, and its standard deviation is about 0.072. How did I find that out? Well, I just I told, in this case I told R, although you could do it with CodeApp as well. I told R to just tell me the mean of all the simulated proportions across all 1,000 simulations that I had to do. And I also told it to tell me the standard deviation of that. So I didn't do that by hand, just to make that clear. But that is the case. So this distribution here has a mean of 0.7 and a standard deviation of 0.072. And so if we were to use the normal distribution to model the shape of this sampling distribution, it would have to look something like this, where we've got 0.7, that's the mean, sitting right here in the middle, right here at the peak of that curve. And then each tick up or down goes 0.072 either away, either below the mean here or above the mean here. And again, if the normal distribution applies, then we would expect that about 95% of our simulated samples would fall within -2, would have a z-score that was between -2 or +2. In other words, the 95% confidence interval, according to the normal distribution, would be 0.555. So this guy right here, all the way up to about 0.845 right here. And that's pretty darn close to the borders of the 95% confidence interval that we got from bootstrapping, right? So this is already a hint that, okay, maybe this normal distribution is actually going to be pretty useful, because if we can find this mean and standard deviation here, then we can just kind of directly read off what the 95% confidence interval would have to be. Now, there is actually a bit of a complication here, because strictly speaking, 95% of a normal distribution is not exactly between two standard deviations. It's actually 1.96 standard deviations of the mean. So if we were to do this with a little bit more precision here than my kind of graph would imply, then we can find the upper and lower bounds of that confidence interval by saying, okay, we'll take the mean, 0.7, minus 1.96 times the standard deviation, and that gives us about 0.558, so a little bit narrower than we had before. Same idea for the upper limit of that interval. We take 0.7, that's our mean, plus 1.96 times our standard deviation, 0.072 again. That gives us a slightly lower upper bound, yeah, a slightly smaller upper bound for our confidence interval here, 0.842. And again, it provides a pretty close match to the upper and lower bounds of the 95% confidence interval that we would have gotten through bootstrapping. Now, to introduce some admittedly kind of confusing terminology that I'm not particularly happy with, the standard deviation of a sampling distribution gets a special name, and that special name is the standard error. Now, like I say, I'm not particularly happy with this, first because it's kind of, we're just increasing the number of terms that have lots of overlapping words in them, which is not particularly helpful for learning and memorizing these things, but it is what it is. But another thing that I don't particularly like is that it's called error. But it's related to the idea that we discussed over the last couple weeks of sampling error or sampling variability, because the standard deviation of a sampling distribution reflects how much variability there is from sample to sample. In other words, how much sampling error or sampling variability there is. And so to call this a standard error is sort of to imply that, well, if our point estimate, our sample statistic is a point estimate of an unknown population parameter, the standard deviation of the sampling distribution tells us kind of how far off we would expect our point estimate to be from that unknown population parameter. In other words, the standard error tells us about how far off we should expect to be from the unknown population parameter if we're using our sample statistic as a point estimate for that unknown population parameter. Now, I mentioned earlier that the normal distribution is sometimes said to be fairly common in the real world. So here are some examples, though, where it may not be so great. So these data come from the American Community Survey. So this is a survey of several thousand American adults. And here is a histogram showing the distribution of annual household incomes across respondents in that survey. And while you might argue that maybe this is sort of a half bell curve, that's sort of like a bell curve that's been chopped off at the bottom, this distribution is strongly right skewed. So this is a case where the normal distribution would not really be able to accommodate the shape of this distribution here. Here's another variable from the American Community Survey. This is self-reported racial category, and here this is, we see, okay, white, black, Asian, other. This is just how they happen to record it for the purpose of this survey. And even though this kind of looks like a histogram, really this is a bar chart, because you'll notice that the x-axis here are not numbers anymore, they're categories. So the normal distribution is just not going to be useful for us when we're trying to model variables that are categorical. The normal distribution only works if we're talking about numbers. So numbers could be means or proportions, things like that. So even when we're talking about numbers, though, here's a bit of a tricky one. This is a distribution of number of hours worked per week, and this big spike here in the histogram corresponds to 40 hours a week, as you might imagine. And there is a big spike, and it's got some tails that sort of fall off roughly symmetrically to either end. But even here, the normal distribution is not going to be a good fit. So here I've just drawn the normal distribution on top of this histogram, and the problem here is that the middle of this distribution is too strongly peaked. The normal distribution has a characteristic shape. It always looks like that. And so it's not going to be able to accommodate any kind of symmetrical distribution, only certain ones that have this kind of consistent shape. So I bring that up because, as I mentioned, the normal distribution is a model, it's an approximation, and it's not always going to be a good one. And only sometimes will the normal distribution be a good model of how individuals vary within a population. That said, the normal distribution is often, and we'll see shockingly often, more useful as a model of how different samples from a population will tend to vary. In other words, the normal distribution is more often a good model for the shape of a sampling distribution, not a population distribution. And the reason why it works that way is due to a mathematical regularity that referred to as the central limit theorem. And that theorem is kind of visually illustrated over here on the right with this little, or excuse me, on the left with this little kind of simulated Plinko game, which we'll get into a little bit more shortly. So this is kind of a hint here about what we're about to do. Now, this theorem, although it has kind of a very imposing mathematical name, the important thing to remember for our purposes is that this theorem applies only when particular conditions are met. So the sampling distribution of a proportion or a difference in proportions can be approximated by a normal distribution as long as there are two conditions that are satisfied. First, observations need to be independent of one another. By independent of one another, I mean that one observation can't influence another. And something like that might happen if, for example, you were conducting a survey and one respondent was able to tell another respondent how they should respond. So that would mean that their two responses were no longer independent of one another. They would be correlated, they would be dependent on one another. So the kind of typical way that we ensure independence of observations is by random sampling or assignment. So this is again where randomness is our friend, because if we randomly sample people instead of say like sampling two people next to each other on the street, then it's more likely that the responses of those two people are going to be independent of one another. They're not going to be able to influence one another. So that's one condition. The second condition is that our sample needs to be sufficiently large, and sufficiently large is admittedly a vague term, and what counts as sufficiently large typically depends on rules of thumb, and in specific examples we'll define some good rules of thumb as we go. But these are the two basic conditions that need to hold for the central limit theorem to apply. In other words, these are the two conditions that need to be met before we can be comfortable using the normal distribution as a model for our sampling distribution. So to get a little bit of hands-on practice with this, I'll kind of show an example of this for now, but I'll let you play around with it on your own. There's a cool little app here, and I will show you how it works in a second. But what it does is allow you to kind of simulate your own little Plinko game, like over here. So just let me click on this link here, bring this over. So first we're going to click on lab here. And you can see that it kind of looks like a little Plinko game, like so. Now, what we're going to do is use it to replicate the four person sampling idea that we began today with. So to do that, we're going to say that there are 4 rows of this Plinko thing. You'll notice that now we have some bins down here, 0, 1, 2, 3, 4. Binary probability here, we're going to keep that at 0.5. The rest of this we can kind of keep as it is. And so you notice what just happened is that the ball dropped from the top. It bounced in some kind of particular random, somewhat random directions each time it hit one of the pegs until it eventually landed in one of the bins. Each time we do that, the ball is going to land in one of the bins, and here if we click this many balls kind of radio button over here, and just kind of let it go. Here in under this n number, you can see the number of balls that have been dropped from this Plinko game. And now, okay, this is cool, but what this is doing is simulating the outcome of asking 4 different people a yes or no question, and then keeping track of what or how many of those people said yes to that question. And the probability of someone saying yes is given by this value here. You'll notice that as we keep doing that, as we keep running all these simulations, we begin to see a histogram of results that has a nice kind of consistent bell curve. And actually we can overlay what that long run bell curve would look like if we click this little button over here for ideal, and you can see that we're already pretty close to that right here after about, say, 600 observations or so. So what I just did there was basically the first 3 steps of this little activity here. And so one thing I'll leave for you guys to do to sort of explore the consequences of this is to first keep the sample size at 4, but then assume that the population proportion is 0.25 instead, and then run that same set of simulations. And then see whether it settles into a kind of bell shape or not. And you may have already guessed by the way that I implied that question, it's not going to get quite bell-like. And so I wanted to think about why that's the case. So why is it the case that it looks sort of bell-like when the population proportion is 0.5, but not when it's 0.25? Then, the next bit of your activity, I want you to keep the population proportion at 0.25, but then try increasing the sample size. And by sample size, I mean the number of rows in the board. So if you keep kind of putting that larger and larger, check and see how long or how large it needs to be before the histogram of simulated results ends up looking at least approximately normal to you. And let's see what you can find for the smallest sample size that produces a roughly normal looking histogram when you let the Plinko game kind of play out as you do. All right. So before we depart the normal distribution for today, I'm going to go through 2 examples of how we can use the normal distribution to do the same kind of inferential statistics that we have been doing so far, namely hypothesis tests and confidence intervals. And the example is based on the following research question. are boys and girls born in different proportions? So first, we're going to think about, well, okay, what are the null and alternative hypotheses that correspond to this research question? Don't you think about that for a sec? Also, do you have a guess about what the answer to this question might be? In other words, do you have some expectation about whether boys and girls are born in different proportions or not? So, here's our null hypothesis, just written out in words. The proportion of male births is equal to the proportion of female births in the general population, whereas the alternative is that the proportion of male births is not equal to the proportion of female births in the general population. So by not equal, I mean it could be either above or below. And this exact question was addressed by an early British statistician, John Arbuthnot, shown here in this very fashionable turban. And the data that he was working from were baptism records from London, so a large city in England. And he did it for a number of years. These are the data from the year 1703. And his data were just this, the number of boy births and the number of girl births recorded as such. So before we kind of get into the example, I'd say it is worth thinking about whether the way Arbuthnot collected his data, whether this sample is representative of all of the people born at this place or time. And when you think about that, it's also worth thinking about how far should we generalize any conclusions that we may draw from conducting a test of this null hypothesis using the data from Arbuthnot's sample. All right. Now, our kind of first thing to do when we're confronted with this kind of data is to ask, okay, well, what is the point estimate? In other words, what is the sample proportion of boy births? And we could do this with girl births as well, but yeah, either way, it'll work out for us. And we can find that by saying, okay, well, here's the total number of boy births, and we divide that by the total number of both boy and girl births here. So 7765 divided by the sum, and that works out to about 0.503. So that's a proportion that's slightly higher than half, which would be 0.5, but doesn't look like it's necessarily that much larger than a half. That said, maybe it's still large enough that we could reject the null hypothesis. Maybe it's large enough that it's still bigger than a half. And to find that out, we're going to have to model the sampling distribution. We're going to have to imagine how this result could have turned out differently so that we can figure out whether this particular result counts as unusually high or low relative to what we would expect to see if the null hypothesis were true. So, as I mentioned, we're going to work through examples of using the same data to do two different things. One, to do a confidence interval. So, generally speaking, for a confidence interval, we can either simulate, or as we're about to do, use a mathematical model to find how this estimate would vary due to randomness and sampling from the population. And that requires us to use the sample to estimate the population from which it was sampled, in a sense. With hypothesis testing, it looks somewhat similar. We're simulating or using a mathematical model to find how this estimate will vary due to randomness and sampling from the population, but when we're doing a hypothesis test, we're not basing our simulations on how the sample looks. We're basing our simulations on how our sample would look if the null hypothesis were true. The point being that even though we're going to be using the normal distribution in both to do both a confidence interval and a hypothesis test, the mean and standard deviation of the appropriate normal distribution are different for these two different applications. So we'll see that in a second. So we can first start with the confidence interval application. Here again is our data from John Arbuthnot. Here's the proportion of boy births in our sample. This is our point estimate. And we can always use bootstrapping to build a sampling distribution and find a confidence interval. That's always going to be allowable to do. But if we want to use the normal distribution, we need to go back to those two conditions from the central limit theorem. So the first condition is independence, and this is satisfied if the observations come from a simple random sample. So for this purpose, we'll assume that that's true, although there's some potential differences there, depending on, for example, if you have multiple births from the same family, they may not be independent of one another. But but we'll assume that that's true for the time being. The second condition is that sample size is sufficiently large. So for proportions, in other words, for constructing a confidence interval with data that kind of looks like this, where we have counts from two different categories, sample size being sufficiently large is checked with what we call the success-failure condition. And all that means is that the number of each outcome, so either, sometimes these are called successes or failures, but whatever it is, so the number of boys, the number of girls, the number of each of those outcomes has to be at least 10. That's the rule of thumb. And obviously that's satisfied in this case. We've got over 7,000 of each, so we're good in terms of the sample size being sufficiently large. And if those two conditions are met, then the sampling distribution of a proportion can be approximated by a normal distribution with a mean that is equal to the point estimate, p hat here, and a standard error, that is to say variability, equal to the square root of the point estimate times 1 minus the point estimate divided by n, the total sample size. So n in this case being 1,500 or 15,448. So let's carry through those calculations here just to see those worked out. So to find our standard error, we plug these guys into our formula here. Here's our total sample size down there. And the standard error is about 0.004, so fairly small. Now, here's our friend, the normal distribution from before. And so we put our sample proportion here in the middle, 0.503. That's at the peak of the curve. That's because that's the mean. And now each tick out is either decreases or increases by 0.004. So 3, all right, go down a little bit more, down a little bit more. And here we go, up a little bit, up a little bit, up a little bit more. And what this represents is basically the different ways that these baptism records could have turned out. And so our question is, well, given that these are this represents the distribution of all the different ways that our baptism records could have turned out, what is the kind of range that encompasses the middle 95% of all of those different possible outcomes? Well, as we saw last time, that's in 1.96 standard errors of the mean. So the bottom of that interval is going to be p hat minus 1.96 times the standard error, and the upper end of that interval is going to be p hat plus 1.96 times the standard error. And that gives us a 95% confidence interval that goes from about here, so 0.495, all the way up to 0.511 up here on the high end. And so, given that this is the case, 0.5, so 1/2, is a plausible value for the population parameter given our sample. It falls within the 95% confidence interval. So it's one of it's not something, or yeah, it's something that we think is a plausible thing to believe about the proportion of boy births relative to girl births in at least the British population in the 18th century. So on this basis, we would probably not feel comfortable rejecting the null hypothesis that boys and girls are born in equal rates. But let's see how we can do the same sort of logic, but now instead of doing a confidence interval, we'll do a hypothesis test. So we haven't really done this so much yet in class, but it is the case that we could use bootstrapping to build a sampling distribution that was based on a null hypothesis and find a confidence interval in the same way. The conditions for using the normal distribution to approximate the outcome of that are the same as for confidence intervals. So again, we have to have independence. So our observations all need to be independent of one another. This is usually the case if they come from a simple random sample. And also our sample size needs to be sufficiently large, which again, for the purposes of data like this, means that the count of outcomes in both categories needs to be at least 10. Well, actually it's a little bit more complicated than that, because the number of each outcome that is expected according to the null hypothesis needs to be at least 10. So what do I mean by that? Well, we'll see that in a second when we go through the calculations, but if those two conditions are met, the sampling distribution of a proportion can be approximated by a normal distribution with a mean equal to what the proportion would be if the null hypothesis were true, so we sometimes write that as p0, and a standard error equal to the square root of p0 times 1 minus p0 times, or excuse me, divided by the total sample size, n. So you see, all we've done here, relative to what we did for the confidence interval, is replace p hat with p0. So that's probably the easiest way to think about this. And the reason we did that is because for a confidence interval, we're asking what happens if our sample is representative of the whole population. So we're basing everything on our sample. For a hypothesis test, we're basing everything on what the null hypothesis says about our sample. So yes, that's p0 down here. All right, so what is this idea of the sort of expected number of successes? Well, expected number of successes, and again, it's called this for sort of arbitrary reasons, but basically each outcome that we could have, the expected number of successes is that p0, the null value, times the total sample size. And the expected number of so-called failures, or just basically the other category, is 1 minus p0 times the total sample size. So in this case, that would correspond to 1/2 times 15,448, because that's the total number of births here. That's the total sample size. And that gives us 7724. And because 1 minus 0.5 is also 0.5, then we have the same number of expected failures. Of course, yeah, again, I don't like calling it successes and failures, but that's unfortunately the terminology that we have in statistics. The point being that the expected number of both female and male births here works out to a large number, and both of them are bigger than 10. So we're in the clear as far as that goes. So let's carry through the rest of our calculations here. So this time our standard error is now 0.5 times 1 minus 0.5 divided by 15,448 and take the square root, which gives us, in the end, 0.004 as our standard error. So again, this actually ends up being pretty similar to what we got last time, certainly up to 3 decimal places. And here's our little normal distribution here. But now, what we're looking for is how extreme our observed proportion, 0.503, is relative to what we would expect to see if the null hypothesis were true. And we can see that here the kind of z-score of our observed value relative to the space of values, or the distribution of values that we would have expected to see, works out to be about 0.660. So again, that's kind of within within sort of the middle bulk of the distribution here, and that is a strong hint that this sort of result is actually pretty common, even if the null hypothesis were true. So even though we got a proportion that was slightly higher than 0.5, it's not so high that it would be out of the realm of possibility. So is this result unlikely enough that we would reject the null hypothesis? Well, no, I don't think so. Yeah, and that's reflected here by the magnitude of the z-score. The z-score is close to 0.5. And so that kind of concludes our tour of the normal distribution as a model for a sampling distribution. And to sort of get some practice with that, we have a new learning check that'll be due by start of class next Wednesday, so that's October 18. As a reminder, also we have questions from our previous lab 6. If you haven't gotten those in yet, are due by the start of class next Monday, so that'll be the 16th. And be sure to keep up with our reading. We're up to chapter 8 now, so there's a lot more stuff here about the normal distribution to deal with, and we'll be getting some more practice with that as we go. So with that said, thank you very much for your time, and happy stats to you all.